phone. If you do me dirty, don't blow up my phone. Poison myself with the thoughts in my head. Doesn't feel good when you know you alone. On my soul, I can't lose control. When y'all do the most, what's my...
What is good, YouTube, man? We are back with another video, man. Today we have Arvin Ash. All physics explained in 15 minutes, worth remembering. Considering that I'm taking college physics course, I figure I might as well spend some of my free time in this. So, got my notebook, got a pen, and I'm gonna watch a physics video for 15 to 17 minutes, and we're gonna see what's worth remembering. Let's do it.
This video is fun.
Consider like, commenting, subscribing. On the road to 999. Turn on notifications if you mess with the content.
I recognize that the vast majority of people don't need to understand all physics and all its complex mathematical. People don't need to
Hey, what's the difference?
teach physics in less than 20 minutes. I recognize.
Okay, peep. So, bro, right here has. Hold on 1 second, yo. Alright, yo, I'm back. I had a technical difficulty, but you know what I'm saying? I got my arrow now, man. Alright, so peep game, bro. Alright, so boom, look, he has a wall here, so the light can't go through. You know what I'm saying? But he doesn't have a wall, and it seems to be that he's changing this angle a little more out, so it'll go further. My hypothesis. Let's get into it.
The vast majority of people
Peep.
don't need to understand.
Or not, it's just going farther. It was the animation, my bad.
Physics and all its complex mathematical glory. But I do think that
Okay, M. Okay, P. What they change?
understand all physics and all its
Ready?
complex mathematical.
Change in X, change in P is greater than or equal to H over 4 pi, man. So people they change the change in P
glory. But I do
to M times V. There's a reason for that.
think that it helps to know a little bit of
It's
physics because
equivalent.
it is so part
M
of your daily
equals
life.
P
Physics
delta
is at
V,
the core of
not times
reality.
delta.
It is
My
the
bad.
core basis of just about
P,
all the
change
experimental
delta P
sciences, biology,
equals
chemistry,
M delta V.
medicine, architecture, geology, meteorology sciences,
What's
biology, chemistry, medicine.
But I'm being looked at weird. Is there a problem?
No, I'm just watching you.
I'm reacting to a physics video because if I'm gonna do it anyway, if I'm gonna watch these videos anyway on my time, and I'm gonna react to videos anyway on my time, I'm gonna do them both at the same time. There are other students who have college physics courses that go through confusion.
It is
so,
5:28
you know what I'm saying?
on a Saturday.
I know it's 5:28 on the Saturday. It's the grind, man. It's the grind.
Okay,
I'm gonna get back to it.
I'm gonna make a sandwich.
Y'all see the grind, man. 5:28 a.m. Don't mind that.
Architecture,
Architecture, geology.
meteorology, and all engineering disciplines.
All YouTubers
So I don't
definitely
want
need to
to simply
understand
give
college
you a
physics.
list of physics. You can easily
Totally.
find that on
Great.
Wikipedia.
Wikipedia,
I'm
man.
going to explain
Wikipedia
what I think
videos
are the
come
most
very soon.
essential concepts worth knowing.
Like,
Let's face it, most
can't even read that.
people who take college or high school physics are going to forget most of it after a few years anyway. Unless, of course, you're a teacher, have a technical job, or make YouTube videos. So I'm going to explain only those things I
See,
think
it's because I make YouTube videos. I need to understand it.
are the most worthy of remembering all of physics.
Watch the ad.
That's coming up.
I'm not even skipping that. I don't even have an ad block. I'm not getting YouTube Premium, nothing right now. Maybe in the future, man. Let's skip it. You got complex questions explained simply. That is what we're here for.
There are 5 broad areas of physics that I think you should know a little bit about. Classical mechanics, energy and thermodynamics, electromagnetism, relativity, and quantum mechanics.
Alright, hold up. Alright, continue.
Classical mechanics are probably the most pertinent to your everyday experience. Here we have to introduce the father of classical mechanics, Isaac Newton, arguably the greatest scientist of all time.
My man's
There are
learned
2
gravity.
main concepts worthy of
He discovered
remembering.
gravity.
The first is embodied in Newton's second law. Force equals
mass times acceleration. I knew that.
This is a deceptively simple equation that has some huge ramifications. Force in classical physics just means a push or pull.
Work.
Mass is a measure of inertia, how much something doesn't want to change in motion. Acceleration is how rapidly your something doesn't want to change
not gonna
in motion.
get in the way of y'all notes, man. If y'all notes, hold up. I'm clicking my ass, man. Stop. My fault, man. Where were we? I apologize. Right here, man. Alright, hold up. See, y'all get the little, you know what I'm saying? So you get the full idea. Alright, let's go. Let's keep going. Let's do it.
Something doesn't want to change in motion. Acceleration is how rapidly your velocity is changing. If you apply a force to a fixed mass, it tells you how much acceleration you will get. And knowing acceleration, which is the change in velocity, you can make predictions, like where an object will be at a certain time and space. So with this simple formula, for example, I can predict exactly where this basketball is and where it's going.
Basketball is really physics,
if I know all the forces acting on it, including the
buoyant force, bro. That's the normal force. How is that the buoyant force? Bro, because people, usually when you draw a free body diagram, man, let me get my little arrow out for you. You know, you have a frictional force or a drag force, you know, the opposing way, you know, obviously it's cutting through the wind, right? You see the spin, you know, that's totally understandable. Gravity, obviously down, you know, negative 9.8 or negative 10, further used, you know what I'm saying? At the speed going forward, obviously, because, you know, you're thrusting the ball forward. This is usually a normal force. Why are they calling it a buoyant force? Isn't a buoyant force when it comes to, like, water, fluids? I may be incorrect. I'm not a physics major. We'll get into it.
Friction of the air, which is also
college physics, not that easy, bro.
Exactly whether or not
we'll learn,
it goes through the
we'll learn today.
The same formula can be used to determine how much reinforcement you would need to build a bridge and how to calculate the lift of a rocket. It's an extremely powerful
Look at that free body diagram. That was a great diagram. You see it?
equation. Force is not a material thing. It is a measure of interaction.
It's a measure
Your
of
body
interaction.
does not have a force. It has a mass. Your weight is the force your body exerts on the ground. Technically, you don't.
9.8. We use 10 now. And, you know, curriculum for physics, man.
Weigh 80 kilograms because that's your mass. You should be saying you weigh 784 newtons, which is your mass times the acceleration of gravity on Earth, 9.8 meters per second squared.
Shout out
to give you an idea of scale, 1 newton of force is equivalent to the force you would feel on your palm if you were holding a small apple. The second equation, also from the...
Is it because the apple thing? That's actually dope. If that is... Okay, F equals G M1 M2 over D2. I have that in my notes for physics.
Is the law of universal gravitation. It allows us to determine the motion of heavenly bodies, like the moon orbiting the Earth, or planets orbiting stars. These bodies, like the moon orbiting the Earth, or planets orbiting stars, it basically says that the gravitational attraction between two bodies is the product of their masses divided by the distance between them squared, times a constant, called Newton's gravitational constant. It tells you that the gravitational attraction diminishes rapidly as objects move apart because it's proportional to the inverse of distance squared. This was a revelation when Newton formulated it because it explained mathematically the movement of all heavenly bodies. It still works well today. The ideas around energy came about 100 years after Newton. It may be the most important idea in physics. Energy is not a vector like force or momentum. It doesn't have direction, but it is a number. Work is closely related to energy. It has the same units. Work is...
It's a scalar, not a vector. A scalar and a vector are the same thing, except a vector has a direction. A scalar is just a magnitude.
Force times distance traveled.
Or I switched them up. I'm pretty sure it's like that.
1 Newton times 1 meter is 1 joule. If you lift a small apple 1 meter, that means 1 joule of energy will work.
Yeah, right. I checked my notes. A scalar, no direction. You know what I'm saying? With the number, it's just a number. And a vector is direction and magnitude.
Energy is really a measure of how much work you can do. Work is simply transferring energy.
Work equals
from one
energy.
form to another.
Okay. 1 Newton is 1 meter equals 1 joule. Joule is heat energy.
For most objects consists of kinetic
heat energy is like kinetic energy. Exactly. I knew that, bro. Bro, I knew that. Tell me now, yo. Energy in, potential energy out. Okay, so you got PE at the maximum at the top. PE max is at the top because it's the most energy for it to go up or down. That's what it looks like with the bike, diagram. The kinetic energy on the bottom and top. I remember because I drew a similar design. See if y'all can see it. draw this way. No, I'll say PE energy sideways. I'm drawing backwards, y'all. Hold up. I'm saying. Y'all see it. I learned this back in high school chemistry, man. Kinetic energy is on diagonals, etc., man. PE is sideways. Pretty often. Pretty often. It's not always, but it helps remember. Alright.
Energy plus potential energy.
Yes, sir.
Kinetic energy is the energy of motion. It is expressed as 1/2 times the mass times the velocity
1/2
squared.
times v squared.
The more mass you have,
I learned that in class.
and the more velocity you have, the more energy you have. Velocity makes a bigger difference in energy than mass. Going from 80 miles per hour to 60 miles per hour reduces your car's energy by almost 50%, which means that in an accident, you have a much higher chance to survive going 20 miles per hour slower. If you're carrying your phone and you accidentally drop it from rest onto concrete, the phone is probably going to get damaged. But where did the energy come from to damage it? The phone had what is called potential gravitational energy.
That's what I was about to say. Because I'm pushing on. Because the gravity was going down. But it wasn't 100%, right? It was potential. Most likely.
When you were
Wait, I'm done. I'm just playing. But it's definitely potential gravitational energy. I was about to say that. I'm just playing because it's going down. So I'm playing.
holding it near your ear. The potential energy was converted to kinetic energy as it fell. Gravitational potential energy is expressed as mass times the gravitational acceleration times the height.
MGH.
This is really another way to express force times
PEG
distance
equals
for work.
MGH. Write that down.
Potential energy gets converted to work or a force acting on
Put
the
it
glass,
down.
which breaks it when the phone hits the floor. So the total energy of an object is both kinetic energy plus potential energy. Potential energy can take many forms. Gasoline or petrol, for example, has chemical potential energy. The biggest thing you should remember about energy is that it's always conserved. It's not
Conservation of energy. I've learned about that in class too. Energy is neither created nor destroyed. Only changes forms. In case y'all can't see it, man, I'm reading it for you.
created or destroyed. It only changes form. Now, talk about energy leads naturally to thermodynamics, which
That's
is the
heat.
study of work, heat, and energy in a
I
system.
knew it.
The
We learned
biggest
that in
concept
class.
worthy of remembering is
P game. Closed system. Hold on, let me get my arrow back before y'all. You know what I'm saying? Educational, man. Alright, open system. Heat transfer clearly. Cold air coming in, hot air coming out. Boom. Mass transfer, heat transfer, etc. Closed system. We got a little closed right here. You know what I'm saying? Heat transfer, no mass transfer. That's important. And we got isolated system, no heat transfer, no mass. This is your thermal. You know what I'm saying? What's it called? Thermal. I'm tripping. You know what I'm talking about? I was about to say thermostat, but the word slipped my mind right now. But you get the idea.
flow of heat. We define energy as how much work you could do.
Thermos.
But another form of energy
Yeah.
is thermal energy. If a car is moving and you apply the brakes, the kinetic energy of the car becomes zero. Where did that energy go? It didn't go into gravitational potential energy, and it's not stored in the car somewhere. Did it disappear? No. It was converted to thermal energy, created by friction of the car's brakes.
I knew that.
Heat
I was
is
thinking.
a flow of thermal energy from one
I was still
object
thinking. I
to
didn't want
another.
to be wrong.
Thermal energy created by the brakes raises the kinetic.
Just for all y'all here watching this video, that be in class, and they ask you a question, you don't want to be wrong, but you know it. It's for you, because I knew that one too.
Energy for movement of molecules in the air. This results in a temperature increase of the surrounding air. This is ultimately where the kinetic energy of the car ends up.
Write down all these notes, man.
The temperature of a system is the average kinetic energy of atoms in the system. Thermal energy is the total amount of kinetic energy of atoms in the system. Another concept in thermodynamics.
I know the video is longer than
idea
15 minutes,
of
trying to get y'all
entropy
educationalized,
is a
man.
measure of
I know
disorder,
I made up the
but
word.
more accurately, it is a measure of the information required to describe the microstates of it.
Alright. Pardon me, man. I'm back. Let's go.
The system. The second
Can I
law
grab
of
that?
thermodynamics
Sure. I'm back, man. My fault.
states that the entropy of an isolated system can never decrease. If you put two liquids together in a bucket, and one is very cool and the other is very hot,
Open system.
why can't you get it such that the cold part gets colder and the hot part gets hotter?
You see it.
Energy could still be conserved.
It transfers
because
between each
the
other.
increase in thermal energy of the cold water could be offset by the increase in thermal energy of the hot water. The reason this does not happen is because of the second law. The universe is on an inexorable path to higher and higher entropy.
I'm just gonna keep the
or
arrow on the
more
side.
disorder. Practically, what this law tells us is that some energy is more useful for doing work than others. Energy
I'm gonna read it for y'all because y'all can't see it. Energy at lower entropy can do more work than energy at higher entropy.
at lower entropy can do more work than energy at higher
That's what he
entropy.
just said.
For example, the energy stored in gasoline is more useful for doing work than the thermal energy that is dissipated from the brakes of your car.
That makes
And
sense.
orderly energy is more useful than one that is less orderly. The heat and exhaust from the car will not spontaneously rearrange itself
True.
to become the
That
gasoline.
is true.
The
Stop.
gasoline can be converted to heat and exhaust. It's important to remember the words isolated system. If you put a glass of water in the freezer, it will decrease the entropy. But the inside of the freezer is not an isolated system because the refrigerator uses energy from electricity to cool the inside. It increases entropy of the room by heating up the room more than cooling what's inside the refrigerator. You should also remember this fact. The one-way flow of entropy appears to be the only reason we have a forward direction of time. Electromagnetism is the study of the interaction between electrically charged particles. The essential
Formulas here. Feel free to write them down. I'll pause for you. And we're back.
concepts are embodied in Maxwell's equations. Objects have something called a charge. We don't know what it is. It's just a property of certain types of matter, such as electrons. If a large object has a negative charge, this means it has more electrons than protons. The first concept I want you to understand is that if you have a static object with a charge, it will affect only other charges. And if you have a static magnet, it will affect only other magnets. It will not affect other charges.
You see how the opposite charges attract and negative charges repel. Or
But if you have
like
a moving
charges,
charge,
not opposite.
it will
I mean,
affect
not
the magnet.
negative,
And
opposite.
if you have a moving magnet, it will affect the charge. At the simplest level of description, that's what these four equations are all about.
Magnetic fields.
The first equation tells us that if you have an electrical charge,
Write it down.
there will be an electrical field emanating from it. The second equation is basically the same concept for magnets, except that magnets will always have as many field lines going out as coming back in. Another way to say this is that magnets will always have two poles, a positive and a negative pole. It can never be a monopole. You can keep breaking up the magnet, but it will always form a new magnet with two poles. The third equation says that if you move a magnet, it will create an electrical field.
Faraday's law.
This means that
We
if
did that
the
in
charge
class.
is nearby, it will feel a force. This is how electricity is generated, by moving magnets. The fourth equation says that a moving charge or moving electrical field creates a
Pause to write.
magnetic
I'm not
field.
pausing anymore.
I
It's
want
a
you to
long
take
video.
note of the constants
Pardon me, I
mu
know it's a
naught
long
and
video, man.
epsilon naught, which are the permeability and permittivity of free space respectively. These two constants determine the speed of light because they measure the resistance of space to changing electrical and magnetic fields. This brings us to Albert Einstein and his theory of relativity, who ushered in a revolution in physics. Interestingly, the title of his 1905 paper on special relativity was called On the Electrodynamics of Moving Bodies. This tells you how tied this theory is to Maxwell's ideas. Einstein thought that if the speed of light was determined by two constants, mu naught and epsilon naught, then the speed of light is a constant too, and may not change in any frame of reference.
Speed of light in vacuum does not change. I was aware of that. I'm just reading it for y'all since you can't see what's missing. So y'all can see what's missing. Velocity equals, velocity, right? Then you got 1 over v squared equals u sub 0 EO or sigma. I'm not sure what that E is, man. And then v equals square root of 1 over u sub 0 E0. I'm not sure what the E stands for. I'm aware it's like a Greek letter.
This was one
Speed
of
of
the
light.
postulates of special relativity. The second postulate was the principle of relativity, meaning The laws of physics are the same
That's
for
why we
all
saw
observers
this,
who
okay.
are moving at
I
the
was
same
aware of
velocity.
that. I
relative
peeped this,
to
that's
each
the
other.
animation. That's how
If
the
these two
animation
assumptions
moves.
were correct,
I
this
peeped.
had some
That
major
goes like that,
implications.
this goes like that.
Suppose you're stationary next to a train, moving at half the speed of light,
You see,
and you
Pete?
turn on a flashlight in the direction of the moving
Exact
train.
same time. It's gonna
Suppose
move
another person
because this
is
is
on the train
equivalent.
and turns on an
Because it's a
identical
double.
flashlight at exactly the same moment.
Probably.
If you saw the light beam on the train, you might think that it should be moving at 1.5 times the speed of light, but it doesn't. It moves at exactly 1 times the speed of
Nice.
light. Does this mean that the man on the train sees the speed of light moving at half the speed of light? No, because of the principle of relativity. He also sees the beam of light from his flashlight traveling at exactly 1 times the speed of light, c. This appears to be a paradox. How can these two observations be reconciled? What Einstein showed is that the only way this can happen is if time for the person on the train slows down from the perspective of someone standing still. This was the crucial paradigm-shifting insight that he unleashed on humanity. Time was not fixed, it was relative. Later, Einstein, with his theory of general relativity, showed that using the same general assumptions, there would be no way to tell if you were on an accelerating reference frame or standing stationary on Earth. So for example, if you were on a spaceship moving at the same acceleration as gravity, 9.8 meters per second squared, and you held a flashlight perpendicular to the direction of acceleration, the light would appear to bend because the wall would be rushing upward at ever faster speeds. This means that if you were anywhere on Earth standing still and you did the same experiment, your light beam would appear to bend because the acceleration due to gravity is 9.8 meters per second squared. But since light always takes the shortest path between any 2 points, this means that space-time itself must be bending in order for light to take that path. The bent path is the shortest path, just like the shortest paths on the surface of the Earth are bent. I find it ironic that Einstein, although he was one of the founders of quantum mechanics because he showed that light came in packets of energy called quanta, we now call them photons, yet he largely stayed resistant to the main implications of quantum mechanics, and that is the idea of a probabilistic and non-deterministic nature of quantum particles. There are many equations in quantum mechanics, but in my view, there are 3 principles that are the most important to remember, and they are expressed in 3 equations. The first equation was championed by Max Planck, arguably the father of quantum mechanics. It says that energy is not continuous, but it is quantized. The energy absorbed or emitted by materials can only occur in distinct quanta of energy, and the amount of energy equals the frequency of the radiation times a constant, called Planck's constant. Using this concept, Einstein later showed that a photon is both a wave and a particle. The second idea is expressed by the Heisenberg uncertainty principle. It basically says that you cannot know both a particle's exact position and its exact momentum at the same time. For a particle with mass, this means that if you know exactly where a particle is, you don't know how fast it's going. And if you know exactly how fast it's going, you have no idea where the heck it is. There is an inherent uncertainty associated with quantum particles. The third equation comes from Schrödinger's equation. It basically says that prior to measurement, quantum systems are in superposed states. This means that their properties can only be expressed in terms of a wave function. A wave function, crudely simplified, is a set of probabilities. So for example, in a hydrogen atom, you can't know where to find the electron in advance. All you can know is the probability of where you might find it if you measured it. Prior to measurement, all quantum systems are 3-dimensional clouds or waves of probabilities. The electron is everywhere at once. It's not here or there, it's here and there. This is not a limitation of our measuring devices, it is a limitation of reality. And this is the reason quantum systems behave so mysteriously with double-slit experiment. A quantum system can be an elementary particle like an electron, or even atoms of molecules that are sufficiently isolated. Isolated means they haven't interacted with something that would cause their wave function to collapse. This is the non-deterministic reality that Einstein had a hard time accepting, and indeed many people today still have a hard time accepting. But the universe has no obligation to make sure we feel comfortable about the true nature of reality. Now this is just one bald ape's opinion about what he thinks are the most important concepts in physics worth remembering. So I hope you found it useful. Now if you'd like to learn these subjects more in depth, then you're not going to find a better on-demand video.
Alright, he's gonna support himself, plug his own merch here. Anyway, man, Obviously, you know, you have your own courses, you have your own teachers, you have your own education, man. But I just want to take the time to go through it myself, going through a college physics course, and you know, trying to relate to everybody else out here struggling, man. Or, you know, even if you're doing well, if you wanted to take a look, take a stop by, feel free to like, comment, share, subscribe. Man, I don't usually do very educational content on this channel, man, but I can start. Feel free to drop any other videos or songs or artists you would like me to react to down below, man. On the road to 999. This is about 297 subscribers, man, and we about to just get into it. You know what I'm saying? It is Tyy Wrrld, and I appreciate y'all if you stayed the whole time, man. Drop a W or L in the comments, and I'm gonna catch y'all next time.